So we're going to start off with f of x equals 1 over x, and I want to know, is this a function? Well, let's test this with our input-output test. I'm going to make a table of values with some various inputs and outputs, and we're going to study those. So when x equals 2, f of x equals 1/2. And that is the only output for when x is 2. When x is 5, f of x is 1/5. And one more, when x is -3, f of -3 is -1/3. Each of these inputs have only one output, right? So every input has exactly one and only one output. That was our rule, our definition for functions. So this is definitely a function. It is a special kind of function called a rational function. It's in the form p of x over q of x, where p of x and q of x are both polynomials, and q of x cannot be 0. So look back at our function, 1 over x. It is in the form p of x over q of x. P of x is 1. It's a very simple polynomial with no variable, but it is a polynomial. Same thing with q of x. Q of x is x. Another very simple polynomial, but they are both polynomials. So I want to graph this. First, I want to know what the domain is. So we think about what are possible values of x, or also what can x not be. Since x is in the denominator, x cannot be 0. Our domain is x cannot be 0. The range is a little bit harder to identify. To identify what the range is, let's maybe look at a table of values. So I'm going to make a table of values for x and f of x. And I'm going to start with big numbers for x. When x is 100, f of x is 1 over 100. What about when x is 100,000? Another very large number. When x is 100,000, f of x is 1 over 100,000. So a very small decimal, or a very small fraction. Even when you go to negatives, when x is -100, f of x is -1 over 100. So you might be able to guess what x, or what f of x cannot be. No matter how large x gets, it appears that f of x will never get to 0. It'll become a very, very small fraction, or a very, very small decimal, but it'll never be 0. So that's going to tell us what our range is. Our range is y cannot be 0. So I want to graph this. I want to graph f of x equals 1 over x. With each graph, I want you to start with the domain and range. Let's start with that for every graph. So for this one, we already know domain is x cannot be 0, and range is y cannot be 0. So how is that going to look on our graph? Well, that's going to be our asymptotes. Since x cannot be 0, that's going to be a vertical asymptote through x equals 0. Since y cannot be 0, that's going to be a horizontal asymptote through y equals 0. It's not going to be really seen in this picture because the axes kind of are in place of those asymptotes. So the asymptotes in my picture are the axes. The graph will never touch the axes. So to finish the graph, let's make a table of values. So I'm going to plug in some various x values and we'll see what f of x is. When x is 2, f of x is 1/2. When x is 5, f of x is 1/5. These are the values that we got from our previous table, yeah? So if I plot those 2 points, I get those 2 points on my graph. What about a negative number? When x is 1/2, or another positive number, 1/2. When x is 1/2, f of 1/2 is 1/1/2, which, if you simplify that, 1 divided by 1/2, that is 2. So when x is 1/2, the output is 2. So here's how it's going to look like in this top right corner. The graph won't cross those axes because those are my asymptotes. So it's going to approach those asymptotes, those axes, but never cross. So it's kind of stuck in that upper right quadrant. Let's try some negative x values. When x is negative 2, f of x is negative 1/2. When x is negative 5, f of x is negative 1/5. When x is negative 1/2, f of x is negative 2. So we plot those points. These points are all going to be in the lower left quadrant. And again, the graph is not going to touch these axes. The axes are our asymptotes, so it's going to approach these axes, get very, very close to these axes, but never cross. So this is what the final graph looks like. So one final note on this graph, 1/x. We now know that it looks something like this. It approaches the axes but never touches or crosses them. So this graph has a special name. This graph is called a hyperbola. It's called a hyperbola. And let's touch back on whether or not it is a function one more time. Earlier in the video, we said it was a function based on the fact that each input has one and only one output. But now let's check if it is a function graphically. We're going to do a graphic test. And how did we check graphically? Well, we used the vertical line test. Remember, we used the vertical line, our pen, our pencil, or our finger, and we traced the graph vertically. If our pencil or our pen touched the graph in only one spot, it passed the vertical line test, so it was a function. This hyperbola definitely passes the vertical line test, so it is a function. So here's another example, and I'm going to give you here in a minute an easy way to find domain and range. We're going to start all our problems by first identifying domain and range. And here is an easy way to do that. So if you're in the form ax plus b over cx plus d, the domain is all real numbers except for that which makes the denominator 0. And the range is all real numbers except for the y value a over c. So what does that mean? First domain. Look at the denominator. The denominator is x plus 3 equals 0. So what makes that denominator 0? The value of negative 3. So the domain is x cannot be negative 3. For the range, we're looking for the coefficients of the numerator and denominator. What is the number in front of x? In the numerator, the number in front of x is 1. In the denominator, the number in front of x is also 1. So a over c is 1 over 1. 1. So the range is y cannot be 1. Those are going to be our asymptotes. So we have a vertical asymptote through x equals negative 3, because x cannot be negative 3. And we have a horizontal asymptote through y equals 1, because y cannot be 1. So here's the vertical asymptote through x is negative 3. And here is the horizontal asymptote through y equals 1. So these asymptotes give a nice kind of structure to our graph. And remember, the graph should never be crossing or touching these asymptotes. So to fill in my graph, I'm going to make a table of values. I'm going to plug in some values for x and see what comes out as the output. So first, when x is 2, when you input 2, you get 0 over 5, which is 0. Next, we'll try when x is 3. When x is 3, you get 1 over 6, so 1/6. When x is negative 2, you get negative 4 over 1. So negative 4. And one more. When x is negative 4, you get negative 6 over negative 1, so positive 6. Alright, so we have some points here to plot. Let's go ahead and plot those points. 2, 0, 3, 1/6. Negative 2, negative 4. So here's my lower right portion of my hyperbola. Draw it so it approaches those asymptotes but never crosses. My final point, negative 4, 6, way up here in the upper left. Maybe one more point for good measure. When x is negative 5, we get negative 7 over negative 2, or positive 7/2. So we plot that point. That gives us another point to plot to make this hyperbola appear in the top left portion. So there is your final graph. So let's look at that range concept of A over C in my first problem. In our first problem, we said the range was y could not be 0. Well, let's look at it as A over C. If it's 1 over x, the number in front of x in the numerator is actually 0. There is no x. The number in front of x in the denominator is 1. So A over C is 0 over 1, or 0. So that's how we can come up with y cannot be 0 for our range. Okay, here's another example. This example is a little bit different because we have this minus 1 off at the end. So let's see how that minus 1 comes into play. With all problems, we're going to start with domain and range. So the domain, we're looking for that x value that makes the denominator 0. In this case, it's negative 3. So the domain is x cannot be negative 3. For the range, again, we're looking at A over C. What is the number in front of x in the numerator? And what is the number in front of x in the denominator? Well, in this bubble, the number in front of x in the numerator is 0. There is no x. In the denominator, the number in front of x is 1. So A over C is 0 over 1, which is 0. So what's inside the bubble can never be 0. But that pertains to only the bubble. What's in the bubble cannot be 0. Now, when you minus that 1, if the bubble can never be 0, you'll never have a situation in which it's 0 minus 1. Therefore, y cannot be negative 1. The bubble can't be 0, so y cannot be negative 1. That's how that minus 1 comes into play. So the range for this graph is y cannot be negative 1. Those are our asymptotes. So if we're going to graph this, let's start with those asymptotes. So make your xy axes, and let's plug in those asymptotes. X cannot be negative 3, so we have a vertical asymptote through x equals negative 3. Y cannot be negative 1, so we have a horizontal asymptote through negative 1. That's going to kind of give us a structure for our graph. The graph is never going to cross those asymptotes. Let's make a table of values to get some points. When x is, let's start off with a negative number. When x is negative 5, y is 0. When x is negative 4, y is 1. When x is negative 1, y is negative 2. And when x is 0, y is negative 5/3. And you can check those points on your own if you need a little bit more time. I went through kind of fast just to give us a graph pretty fast. If we plot those points, we get a hyperbola in the upper left portion. And if I plot the rest of my points, we'll get the rest of the hyperbola in the lower right portion. So the graphs approach these asymptotes but never cross. So here's two more examples for you. I won't talk you through it. I'll play some music for you. But here you go.